This science talk video discusses the first structural geology study of Earth from the surface to the core at 2,850 kilometres depth in plans and seismic tomography sections right around the northern and southern hemispheres. Over the last 25 years, my EagleEye Ultra Enhancement system has provided new structural geology data over the whole Earth. This new geology has been published on geotrex.com.au. This new structural geology suggests the current plate tectonics model is flawed and a new tectonics model is proposed. How has EagleEye discovered verifiable structural geology that current geophysical methods have missed? Hello, I'm Bob Watchorn, a geologist with over 50 years experience in all facets of geology. Over the last 25 years, I've developed the EagleEye structural recognition system, with which I have researched all the continents and many mineral districts from the surface to the outer core. The cartoon at the bottom right shows the usual method of geological research, which is generally fragmented and only explores up to continent scale. My research has examined the whole Earth from the surface to the core to get a global overview. This talk is on my structural geology findings. EagleEye system enhancement results. How was the structural geology on the right-hand image of section BB of North Africa achieved from the left-hand seismic tomography image? This will be shown at the end of the talk. The original image details of the African rift. Geology structures is not observed. The EagleEye image detailed strong arcuate and linear structures to 5 to 10 kilometres width are observed. EagleEye global structural geology based research gives a different picture of Earth structure and tectonics from the current non-structural research. This slide shows the plate tectonics model versus the Watchorn block tectonics model. The plate tectonics model is based on mathematical models of different seismic waves velocities, not the Earth's actual structural geology. Watchorn block tectonics model is based on actual structural geology of the seismic tomography sections through the northern hemisphere of Earth. As you can see, they are very different. We will investigate the many differences in the two models during this talk. This slide shows the current plate tectonics model. The Earth started molten with a thin crust. Plate tectonics causes continent building by accretion. The crust is constantly recycled, thus there are no preserved late heavy bombardment impacts, and subductions, plumes, and the mobile mantle transport mass from the core to the surface and back to the core. This slide shows Earth evolution first stage, the Theia impact, from my observations and hypothesis. Earth reformed cooler and brittle 4.47 giga-annums ago, with early evidence of near surface water, and then gradually heated up and cooled again. The reason that it formed cooler and brittle, as you can see in the image on the right-hand side, is because after the Theia impact, it was partially shielded from the sun by the impact debris cloud. The shaded space temperature is -100. Earth evolution second stage. Extended late heavy bombardment forms 600 kilometre depth brittle lithosphere. The Earth formed relatively solid to the core with a thick crust which was thickened by early late heavy bombardment impacts. These huge circular impact structures are still observed under all continents, and it's shown on the right-hand image on Africa at 220 kilometres depth. There's about 5 big main ones you can see and many smaller ones. This slide shows the interpreted late heavy bombardment impacts and later smaller ones. The fact that these impact structures are still circular and overlapping and not hugely distorted at 225 kilometres depth under Africa strongly suggests that the Earth under Africa has not moved in 4.5 billion years. This image shows the African seismic section through West Africa to Arabia, which we'll be examining later in detail. The 225 kilometre depth rings and the cross-section down arcs correlate, suggesting a greater than 4 gigaannum deep impact structures are still present, which negates a mobile mantle. This image shows Africa's genesis and suggested geochronology. I have enhanced the surface Landsat and all the seismic tomography sections down to 400 kilometres depth under Africa. The ring structures are plotted and correlate with the down arcs on the section BB across Africa. I've tentatively assigned geochronological ages from 4.5 gigaannums to 3.8 gigaannums on the right-hand side. I have completed similar exercises for Australia, South and North America and Europe with identical results. The largest ring structures are from 400 to 600 kilometres depth, and they decrease in size to 3.8 gigaannums. We'll now look at global structural geology research using northern tomographic sections. This image shows the northern tomographic sections on oceanic crust topography showing the crustal age. In this exercise, we won't be looking at section 5 across the Pacific. We'll be looking at section 6 and 7 and 8, which go across from North America to Arabia, and on through section 9 through Asia from Spain to Japan. This section shows the seismic tomography from the west coast of America to Arabia. Note on the left-hand side the Pacific subduction zone structures, and in the centre is the mid-Atlantic ridge, and the right-hand side we've got the African collision zone on the under that wavy white line. You can see the Alps nap structure, which is in exactly the right spot from the shallower geophysics. The whole section has brittle structures from the surface to the outer core. We're specifically looking at the North America and Europe section on this West Coast America to Arabia cross section. We're starting to look at the mechanics of the tectonic processes that have formed Earth. Under both the Pacific subduction zone and the African Europe collision zone, cooler upper Earth material is pushed into the outer core, which is at 3,300 degrees centigrade. This huge volume of material would be quickly digested and would pressurize the liquid outer core and thus try to expand the Earth. We'll now look at the mid-Atlantic ridge. The pressurized outer core material will exploit the weakest areas of Earth, and one of these, at the moment, is the mid-Atlantic ridge extension zone. Strong vertical and flat brittle structures can be observed from the core to the surface in the mid-Atlantic ridge. In the mid-Atlantic ridge area, I think the vertical structures are extension structures as the pressurized core expands the mid-Atlantic ridge zone and forces material from the core to the surface. The flat structures shown, I believe, are pressure release pop-up structures. This explains the chocolate block texture that I've seen in all of the mid-ocean and African rift zones around the globe. We'll now look at section 9, the seismic tomographic section from Spain to Japan. This image is from Spain to Japan. The top right image is the original image that the enhanced image was derived from. The seismic section from Spain to Japan is similar in tectonics to the America to our Arabia section, in that it has the African-Europe collision zone in the west and the Japan-Pacific plate subduction in the east. The blue arrows represent colder 2,600 degrees centigrade subduction collision material pushed into the 3,300 degrees centigrade outer core. The heated magma and upward fluid release pressurizes the cooler 2,600 degrees centigrade brittle lithosphere right through to the surface. The overpressurized core causes incipient rifting and plate separation in the center of Russia, shown by the vertical structures highlighted by the light blue lines. There are also many flat structures which, like those in the mid-Atlantic ridge, I believe are pressure release pop-up structures. We will now summarise this global structural geology research using the northern tomographic sections. We have seen that vertical structures extend from the core to the surface. These occur on plate boundaries in the Pacific, as internal plate sutures in Asia, and as mid-ocean rifts in the Pacific and Atlantic. They even push through subduction zones in North America and Japan. These numerous vertical structures right around the Earth suggest that the global mobile mantle cannot exist. I suggest glacier-type block shuffling with lithosphere and inner core accreting. We will now look at global research using the southern tomographic sections. This slide shows the current 3D modelling using seismic tomography. Once again, it's a model based on domains of different speed seismic wave, but does not recognise the Earth's structural geology. This modelling is used to create continents and lithospheres under the Earth. Watchorn block tectonic model, based on the actual structural geology of the seismic tomography section through the southern hemisphere of Earth. So in the last two slides, we've seen the Watchorn block tectonics model of the northern and southern hemispheres of Earth. This plan shows the southern tomographic sections studied. We'll be looking particularly at the Section 3 South American plate. We'll also be looking at Section M for the African Rift and also Section B for the African Rift again. We will now be looking at a closer view of Section 3, the Nazca South American Subduction Zone. This is how the South American Subduction Zone fits into the global structural geology as defined by EagleEye. EagleEye enhancement sharply defines domains with different S-wave properties. The big difference between the EagleEye section and the original image up in the right-hand corner can be clearly seen. There is no structural geology at all on the image that is generally used by geophysicists. What I call blocky icefall subduction material, the blue arrows, is pushed into and melted off by the 3,300 degree centigrade outer core. Heated magma and fluid upward release, the orange arrows, occurs into the 2,600 degrees centigrade solid lithosphere. Subvertical structures cut through the active subduction zone, giving extensional mineralization pathways. This shows the global and very strong nature of the force exerted by the pressurized outer core. This force cracks the subduction zone even as it is descending. There are many flat structures observed on this section, and heat ponds up against these flat pop-up release structures, suggesting that heat is transferred by in situ lithology replacement and not active lava plumes. The blue lines designate the pop-up release structures similar to those in Asia and the Mid-Atlantic Ridge, which dam the upward heat flow. We will now look at global research using southern tomographic sections. Closer view of Section 4MN of the African Rift Zone in Central Africa. We will now examine the African Rift. This figure shows brittle deformation to the core under Africa. Shows subvertical East African rift structures and 600 to 700 kilometre deep bowl structures. A viscous mobile mantle cannot exist under Africa, as there are 2,900 kilometre deep subvertical structures to the outer core. There are also abundant cross-cutting flat structures. These flat structures cut right across the supposed plume area with no real deformation or disruption. So what are currently called plumes are probably forceful upwellings of heated fluids and magma up subvertical structures. Global research using southern tomographic sections. A closer view of the African Rift Zone in Section BB from West Africa to Arabia. The aim of this exercise is African Rift structural verification. The top section of the plan shows seismic tomography to 60 kilometres depth and Section BB across from West Africa to Arabia, and that's from 60 kilometres depth to 800 kilometres depth. Are there correlating structures? This data is from different sources and has been eagle-eyed years apart. This image shows the 440 to 660 kilometre seismic discontinuity, which is well known and is very well shown on the section BB. This section and plan show the East African Rift and the Central Saharan Rift down to 400 kilometres depth, but the structure continues beneath. In both sections, the rift has that chocolate block appearance that we saw in the mid-Atlantic ridge, confirming the similar mechanism for opening with the flat horizontal shears coming through, as well as movement outwards on the rift valley. This image shows ring structures on the seismic tomography at 60 kilometres depth and down arc structures on the seismic tomography section. The down arc structures at 400 to 600 kilometre depth are very clearly seen. There are almost no upward arcs, suggesting all of the ring structures on the plans are bowls formed from impacts and not upward facing domes formed by plumes. This image shows linears or faults, both in plan and section. There's very strong correlation between many of the faults in plan and section, particularly the double fault on the centre right, both correlates in plan and section. A very unusual fault, and it would be highly unlikely to jag this fault position with the data that's been assembled over several years from different databases. The previous slides have confirmed on many levels and with many different structures the validity of my EagleEye structural geology. How was this particular EagleEye structural section generated? The subduction zones are very clearly seen, and the downward movement is brittle movement like a glacier. There are abundant brittle structures extending from the crust to the outer core. These structures cut the plumes, Tonga and Africa. This suggests that the plumes are actually in situ replacement of lithosphere and not flowing. This image shows that the plate boundaries extend to the core. This suggests that the movement of the lithosphere occurs as core to crust blocks, rather than thin surface plates carried along by a mobile mantle. These surface to core structures make the current model of a global mobile mantle, the area in the annulus of the blue rings, impossible. To summarise, I'll now summarise the differences between the current plate tectonics model versus the Watchorn block tectonics model. Earth started molten with a thin crust. I say Earth formed cooler after their impact. It was dust shielded. Plate tectonics crust constantly recycled, therefore no preserved late heavy bombardment impacts. Block tectonics, cooler Earth with thickened solid crust preserved the late heavy bombardment impacts to 600 kilometres depth. Plate tectonics and mobile mantle destroyed deeper structures. In the block tectonics, surface to outer core has brittle vertical structures. Solid continents formed and only now are getting broken up. Plate tectonics, mobile mantle subduction and plumes transport the mass from the core to the surface and back again. And the block tectonics model says that the mobile mantle is not possible. And that's why I suggest there's a block tectonic movement. The following slides summarise my hypothesis of Earth evolution based on surface to core geology of seismic tomography sections to the northern hemisphere of Earth. Earth evolution first stage, the Theia impact. Earth reformed cooler and brittle at 4.47 gigaatoms after the Theia impact because it was partially shielded from the Sun by the impact debris cloud. The shaded space temperature around Earth at the moment is about minus 100 degrees centigrade. Earth evolution second stage. The extended late heavy bombardment from 4.47 to 3.6 gigaatoms forms a 600 kilometre depth brittle lithosphere. Earth formed relatively solid and brittle to the core, with a crust that was thickened by huge circular late heavy bombardment impact structures. Earth evolution third stage. The commencement of subduction and extension tectonics at about 3 to 2.7 gigaatoms. The lithosphere at 2,600 degrees centigrade was pushed into and digested by the liquid outer core, which is at 3,300 degrees centigrade. The outer core is pressurized and tries to expand the Earth. This forces hot core material up extension zones which operate from the core to the surface at the Mid-Atlantic Ridge, the Pacific and Indian Ocean extension zones, and also at the African Rift System. There is no evidence of a global mobile mantle. Summary of global research using the northern and southern tomographic sections. EagleEye does produce verifiable structural geology. We have seen that it produces good structural geology that cross-correlates with the known geology of the Mid-Atlantic Ridge, North American subduction, the African-Europe collision, the Asian-Pacific subduction, South American subduction zone, and the African rift structures, both in plan and section. If EagleEye is producing verifiable and reproducible structural geology, our whole system of global tectonics needs revision. Thank you for listening.